in the San Jose office. So first of all, thank you for staying this late. Hoping that you stayed for my presentation and the next presenter. And thank you, Courtney, for organizing this event. Actually, I recently organized something similar to this at PayPal, and I know that a lot of things goes behind the scene, and it's not trivial. And also, thank you, Paige, for accommodating my slide updates until the last minute. So today, I'm going to be talking about large-scale graph processing and machine learning for fraud prevention. So essentially, two separate topics. So I will talk about graph processing in the first part and how it feeds into our machine learning pipeline to build machine learning models. So this is actually the ROC curve, which we stare at it every single day and every single minute. So it's actually, for those who are not familiar with it, for binary classification model, it's a plot of true positive rate and false positive rate. So what you want is actually, if a 1 means that you have a perfectly classifying model. You can see that this is our current benchmark, which is 0.96, which is pretty good for fraud models. The reason why we started at this is that basically, even though it's 0.96, we continue to invest heavily. PayPal has been building models for over 10 years, machine learning models. Most of our models are the earlier versions, or even prior to deep learning, we had all neural network-based models, which have been giving incredible performance lift. But we reached at a point where our current champion models were saturating in performance. So in order to, but we want to continue to push the model, even though there is not much room, but even a very, very small increment in this performance. Just to clarify that this is not the measurement we use. We have an internal benchmark which I cannot share, but something close to this. The reason is that even if you get a 0.01% performance lift, because of the amount of volume of transactions we process, it results in incredible savings and loss reduction at PayPal. So that's why we have a team of data scientists, over 100 data scientists, and a lot of people working on machine learning research. So in order to push the model, obviously, we need to look at all aspects of the way we are building models. So one of them is actually, obviously, the motivation is around graph processing. So you can think of the world is actually better represented in graphs, right? We are all connected in some way. So this is actually a better figure representation from Professor Luis Couture from UCSC. You can see that what we had was the world was better represented in graphs when we flattened it and put it in a tabular data store, like a relational database, or Hadoop-based store like HDFS. What we did was we lost all that interconnectivity between the data with the tabular data structure. That's because the reason which was done was all this machine learning algorithms require a feature vector. You have series of observations, and each observations, the algorithms assumes that each observation is independent and identically distributed. Obviously, that's not the case. So let's say that the world is highly connected, and what you do now and what you do next is highly connected to what you did in the previous time steps. So obviously, we need a data science for graphs. It's really a growing field. A lot of machine learning data science around the tabular data, but data science for graphs is really emerging now. So we have a large-scale graph processing system that is open source, Apache open source software called Giraffe. It was released by, based on Google's paper, Pragel in 2010. The way it works is actually it's a vertex-centric approach. So essentially, you have a graph, and it partitions the graphs into vertices, and each compute or worker operates on a subset of those vertices. And all the vertex care about is actually it receives message from other vertices, it updates its current states, and sends a message to all the vertices it is connected to. It's a very, very powerful distributed graph processing technique, which we have been using for over 3 years at PayPal. So the way we employ graph processing using Giraffe at PayPal is what we do is essentially we use graph processing to build feature representation from graphs. what we wanted to compute is actually a two-step neighbor. So, for example, let's say I am connected to someone else and someone is connected to some other person. So you want to compute the two. Basically, Giraffe provides a facility to compute n-step neighbors. So what we want to do is, if IP is connected to the intuition behind this is actually people. If you are a fraudster and the chances are, and you are connected to other fraudulent IPs, chances are that could also be fraudulent, right? So the computing those neighbors can actually enrich our models in building better fraud detection models. So what we use is actually we use events from several data sources. For example, we get an event every time a user signs in, sign up, or a payment transaction when actually the transaction happens, and login, logouts. The data, all our data store is actually in Hadoop-based thousands of node cluster HDFS. So we keep a year's worth of data set. For our existing processing, we use only 1 year's worth of data set. We have a series of MapReduce jobs. So this is actually back to the first point I was saying, is that we threw all the data into HDFS and unstructured data store. In order to apply any type of graph computing framework, you need to build the graph from scratch. So we have a series of MapReduce jobs. Obviously, you need MapReduce jobs to do a lot of data cleaning upfront, and you want to join all this 5 different types of event transactions to build the graph. There are several sequential MapReduce jobs which we have. And last 2 jobs we have is a Giraffe-based jobs, so where it computes a two-step neighbor for several entries, like IP address is one entity and visitor ID and so on. This is actually 2-day process. PayPal has billions of transactions, so in order to go through this enormous data store, even with the cluster size which we have, it takes about 2 days to compute this two-step neighbor. So graph processing is not trivial, even with the distributed computing framework around. Obviously, one of the fundamental reason obviously is that first of all, we lost that interconnectivity by storing the data in HDFS. And because of the way MapReduce is built, is a lot of intermediate reads and writes to the disk, right? So you have a lot of I/O, which is actually incredibly slows down your computation time. Plus, because of the thousands of node cluster, you have a lot of network communication. So all that adds up in the computing slowdown which we have. Plus, obviously, anytime you operate a giant cluster, regardless of how sophisticated your cluster management solutions are, it's very unstable. We have a contract with Hortonworks which maintains the cluster, but the Giraffe is not supported by them. So anytime we upgrade the cluster to newer versions, it breaks. So we have to maintain in-house as well because of that. So what we wanted to look is actually how can we actually build a better graph processing pipeline at PayPal. We wanted to take a complete full stack approach. So one other thing with, again, we wanted to eliminate, can we actually represent, we know we are getting a pipe to the events coming in. Can we actually represent this graph in a GraphDB to start with? So a better representation and actually capture the representation as it comes in could potentially improve your computer performance. So GraphDB are the bottommost, but before that, obviously there are a lot of work which is happening in the HPC. So we want to explore on the hardware layer, GPUs, FPGAs, and TPU is a tensor processing unit from Google. On storage, right now, the whole fundamental premise between Hadoop MapReduce is you have a whole bunch of commodity servers with a low quality disk. So instead, if you have a SSD-based storage, could that also benefit the computing processing time? On the algorithmic layer, we want to look at not only at the deterministic graph-based algorithms, we also want to look at probabilistic graph modeling. Obviously, in order to build any type of graph analytic solution, we need a visualization we have analysts to actually who looks at the graphs and manually labels it, and we apply graph processing technique to propagate the label to the other nodes in the network. Eventually, we want to actually, instead of having a traditional machine learning based model to do the prediction, we want graph-based machine learning models to do the prediction, so that when a transaction happens, you can directly query this system, which has got the graph model already built, and you query the graph model to make the prediction. So that's where we are going towards in the future. So obviously, by doing that, why we can obviously we can one of the primary reason is that we can solve problems which we are not able to currently solve because of the compute infrastructure bottleneck. AML, anti-money laundering, is one case where the fraudsters move money between series of networks. It can easily be solved if we have the right infrastructure in place. We can also, collusion is actually, for example, PayPal provides both buyer protection. Let's say you buy something and let's say you are unhappy or you have any kind of complaint, no questions asked, you get refunded 100%, and we also have seller side protection. So what fraudsters do is they capitalize on this buyer and seller protection to, in fact, they will create their own merchant accounts as well as they buy it, or they will get the goods and claim that they didn't receive the goods, but the end result is actually we lose money through this collusion type of frauds. So we can detect all those types of network-based frauds better with graph-based models. So we started doing the quick POC with the stack which I laid out. Right now, at the hardware layer, what we use is a GPU-based. It's NVIDIA's Pascal. It's state of the art, but they already have Voltas out, which is actually we're in the process of procuring it. It's a HPC GPU-based computing from NVIDIA, and we in these hardware we have SSDs. And for the GraphDB used for this POC, Neo4j, which is actually built with, instead of having a distributed database, it's actually meant for optimized for a scale-up model where it's for optimized for a single server solution. On the graph algorithms, the Neo4j has implemented several graph-based deterministic algorithms, which was used for this. Also exploring Gunrock, which is actually an open source framework from UC Davis, which is actually GPU-based graph computing paradigm. This is our cluster setup. So what we want, the issues which I mentioned is that can we eliminate our distributed low quality commodities type cluster, and can we eliminate this MapReduce jobs, which is actually, I think in a way I feel that it helped at some point in time. I think it's, my opinion is that it's creating more problems by we buying, let's just distribute it, processing across all low quality servers, but instead of that you have a one powerful machine, you don't have to distribute, you don't have the overhead of the distributed computing, but you distribute within that single machine. So that's a premise we wanted to validate. So let's see. This is actually statistics available from our graph processing POC. It's 1.5 billion. Currently we have graphs of size 100 billion edges. So, but for the purpose of POC, sample down, see whether there is any even value in going to this route. You can see that most are small communities. The degree is, you can see it's a long tail distribution. So, which is actually traditionally there in any type of graphs you look at this scale. The graph algorithms I looked at is primarily three types of deterministic algorithm. PageRank PageRank is well-known algorithm for computing central influencing nodes in the network, which is Google came up with it. Let's say that if you have IPs which are centrally influential and they are mostly committing fraud, so the chances of whoever they are connected to could also be fraudulent nodes, right? So that's the idea behind it. So PageRank is one type of algorithm we implemented, and the other one is connected components. Connected components helps you to discover subgraphs. So the subgraphs in which each node is reachable by every other node. And community detection we also used for this, actually detecting groups of nodes, which are, especially when they're in the collusion case, you can see that it's a community of nodes colluding with each other. So community detection algorithm helps to detect those clusters. So this is actually runtime performance. Actually, there is a typo here. It's the compute time is actually not milliseconds, it's seconds. For the graphs about 1.5 billion edges. You can see the PageRank. All this computation, all these algorithms, you can see that it's under 10 minutes. So currently, we are taking 2 days to do this exact processing. So, and the page rank actually, it's really under 2 minutes, so you can compute the entire page rank with the assumption that the graph is actually represented in a GraphDB rather than in a HDFS-based storage. And we don't, compute use the Neo4j implementation of graph algorithms. This shows that actually this POC shows that there is a promise in going the scale-up model. Actually, we do see, at least in the Bay Area, there are a lot of move towards a scale-up model where you have a single powerful server with terabytes of RAM, petabytes of RAM too. We have this particular machine has 1.5 tera. We also have machines with 3.2 terabytes of RAM. So if you can fit everything in one machine in memory and you have enough processing power, either with GPUs or multi-core processing, that's saving significant compute cost. So it looks like it's promising. The scale-up is promising in terms of our future direction. So one thing is that people say that the scale-out provides infinite scaling. In my opinion on this is that infinite scaling is kind of a myth, and when we want to do graph computing, we need to look into the fact that people say you cannot put every data in a GraphDB. The data which makes sense to be represented as a graph, it should be there, and anything which is actually non-graph in nature, so you store it in a relational DB. So GraphDB cannot survive on its own. You always need some other supporting database to represent your data. But the data which is our graph in nature, GraphDB is a perfect solution to represent. So the key learnings from this, I already said that you can say that you can fit the entire graphs easily. This is actually the 1 year's worth of data is only 70 gigs. So can, we have 1.5 terabytes of RAM. Easily we can store the entire data, and this 1 year we can expand it to 10 years worth of graph data. So the 100 billion edges talking about, you can easily fit in this machine. Significant reduction in processing time, and you can see that significant value in GraphDB. So one of the things which we do is that once we have the base graph, we create many subgraphs for the analyst to view and reason with. So they want to operate on a subset of the graph to have some understand how our Foster's patterns evolve. So doing this in an iterative fashion, storing the data in GraphDB helps to speed up their analysis efforts. The second part of is actually it's about machine learning algorithms. So traditionally what we still continue to operate the graph algorithms produce feature space, which actually use as feature vector in our machine learning algorithms. The machine learning algorithms I'm going to briefly touch on is active learning, deep learning, and the gradient boosting trees. So our traditional, our current pipeline is primarily, most of the models are built offline, and we have, in the interest of time, I won't go into the detail. It's pretty straightforward in terms of any model development, but one of the things which I would say is that we spend significant time in auditing because when you actually produce a model which produces a score for on a bunch of test data out of time data set, we also want to verify that the model actually continue to function when it's deployed in production. So we collect samples from once the model is deployed in production, whether the distribution or the score distribution matches with what you observe in the out of time window in an offline world. So a lot of work goes on. There's a score level audit, and there is a variable level audit because there's the distribution of the variables. Because the premise behind machine learning models is you have a distribution of the data set which is captured in the training window. You want to make sure that the distribution stays similar when the model is rolled out in production. So there is auditing actually helps to uncover those distribution anomalies. In serial pipeline, mostly the implementation is the productionalization part is still manual in nature. So what we want to do is, so the future actually what we want to do is that we have been looking at for more than a year or so, more than a couple of years on the algorithmic front. Our traditional models are all neural network based. We looked at obviously deep learning and gradient boosted trees and active learning. So we also move in the process of moving towards pure offline learning to online inference to online learning, but online learning is not trivial. We have some kind of batch learning, which is not a true online learning in our production setup. We also want to look at, because there are so many tools evolving in the machine learning space community, so we want, there is no standard in terms of how the spec is delivered, right? So which is actually organization of PayPal or any big companies need to worry about how the underlying specification of the model is represented. PMML is actually one standard, but it's not an open standard. There are other standards actually, but there are so many. I am a firm believer in open source. There is a lot of developments in the open source community, but there is no open standard. This is actually still a work which is actually work for the machine learning community to come up with an open standard. We also want to have an infrastructure. Right now, it's all CPU based for the inferencing. We want to have a production infrastructure which is agnostic to most of the talks and everything you hear is on GPUs and TPUs. Is the inferencing still happens in offline. But in order to have an online inferencing for GPUs and having to have a inference produce, for example, our required SLA is less than 10 milliseconds. Having to have that SLA with this particular stack is not trivial, so we are working towards that. I will briefly talk about active learning. The previous talk also briefly touched on it. The active learning is a lesser known. You hear a lot of buzz about deep learning. Gradient boosting is really an awesome algorithm. Actually, deep learning is highly successful in the image and the voice space. But gradient boosting tree is equally good for, especially for structured data like the transactional data we have. But the active learning is one lesser known machine learning algorithm, which is essentially to one of the pain points of building a supervised learning model is you need labeled samples. So for example, you need to, for the fraud case, you need to know whether the transaction is fraudulent or not. You have to have a human to label it, and imagine that having to label a payment transaction is not trivial, right? So employed active learning, which is actually a very, very lesser known technique in machine learning, but is extremely useful for machine learning community. So let me just skip on the idea behind it is that I'll just give you a simple example on active learning. So you start with a small labeled sample, then you select the idea behind it, you select a sample which is actually, let's say that you have a model which gives you a score of, for instance, it gives you a score of 0.5 on a binary classification. Obviously, it doesn't know whether it's good or bad, right? If it's bad means the score will be close to 1, and if it's good means it's close to 0. So you want to pick the samples which is uncertain about and giving the samples and let this analyst label only the ones which is most not confident about. So that's the idea behind active learning. So I employed active learning to, and the active learning actually in the fraud case, especially our data is very critical. In the image and the voice space, you can actually have Amazon Turk, a stream of people to actually label it. But for a fraud case, it's not trivial. So it requires significant amount of time, and we wanted to improve the quality of our models. So that applied. This is actually an architecture of our active learning framework. So essentially, we employed an ensemble modeling technique using deep learning and GBT model, and use active learning for the labeling part. One of the other key things with active learning is that you cannot have, for a fraud case, label one sample at a time, so use a bagged approach. So you give bags of samples rather than one sample at a time, because we have billions of transactions to label it. So I will skip the deep learning, everybody knows about it. One of the thing I would say is also on the gradient boosting technique in the interest of time. Quickly on the experiments, it's a 1 year's worth of data set with 11 million transactions with features around 500 to 600. Tool, I will spend some time, H2O was a previous presenter. We have been using H2O very heavily since, been involved with H2O ever since the company was created for close to 3 years. First of all, what it appealed to me is open source, but it's an awesome tool where they have some of the state-of-the-art algorithms implemented in this, and we have production implementation of H2O has been running for years actually. So it's a verification of H2O as a very stable platform for production deployment. And also it's unlike scikit-learn, it's highly scalable, so you can can train our models as we expand on the data set. So you can see that with active learning, with the committee-based model where I used an example of deep learning and GPT, the ROC, AUC improved from 0.96 close to 0.98. So this shows the promise of both active learning and along with gradient boosted and deep learning. To conclude, graph algorithms are showing promise, but we are just starting the journey in that space. And deep learning, GPT, we have been having GPT models for a long time. The deep learning based, this particular one is not deployed at production. We have only a GPT based models, so we are working towards the ensemble deep learning and GPT models in production. And the other key finding was scale-up infrastructure. We are moving towards more highly scale-up systems rather than distributed Hadoop-based storage systems. And the other thing we are exploring is a probabilistic graph modeling. One of the things which you required is we want a model to be interpretable, so that is an area of explainable AI, which is also we are exploring to have when you actually reject a transaction, we can actually, the agent can look at it and see why the model thinks it's the score is high. So that's all. Run out of time. So thank you for everyone's time.